Okay, so off we go. We have Lara's second talk, Geometric Tools Lecture 2.
Thanks very much. All right, so I'm going to pick up roughly where I left off yesterday. So quick recap of where we got to. The basic thing that I wanted to introduce you to yesterday was the idea that in a string dimensional reduction, so in general, going from 10 or 11 dimensions down to lower dimensional theories. In our illustration from yesterday, we did heterotic 10D going to a n equals 1 4D theory by choice. The general structure that we observed is that the geometry that you need to consider in order to get compact directions going from 10 down to 4 has to be constrained. Those constraints we can get by, in our case, we imposed the fact that we wanted n equals 1 structure in the solution. So we demanded that the solution to the equations of motion respect the symmetry of the theory, at least part of it, giving us a supersymmetric theory in 4D. And what we saw was that this leads to a characterization. If we write M10 as M4 cross M6, these fermion variations that come from your supersymmetry transformations lead you to an M6, which gives you the idea of G structures. So very loosely, G structures are the existence of a nowhere vanishing spinor of a particular type. There's these twisted covariant derivatives that we saw appearing in the equations of motion. And basically this kind of flow, here I illustrated it for heterotic, but going from 10 or 11 dimensions down to 4, this happens for basically all flux compactifications of string theories that we're familiar with. So if you're asking for sort of the most general dimensional reduction ansatz that you can do that preserves some supersymmetry, this is the game you're going to be playing. And because we were interested in 10D heterotic going to a 4D effective theory, specifically we were interested in SU3 structures. And what we found was that using our nowhere vanishing spinor, we had two objects that mattered to us, a 2 form and a 3 form, and that these two guys can be one-to-one and constructed from torsion classes Wi. And there are 5 of these in the SU3 structure case. 5 here. So let's say we were doing some other dimensional reduction. Let's say we were doing M theory on a 7 manifold to get down to a 4D theory with general flux backgrounds. You can also have G structures there, but the torsion classes that you would use to characterize it would not be these 5. There would be a different set in that case. So the fact that we have SU3 here was what gave us this interplay that we played with last time. Okay, just a couple words about this geometry. The thing that we left with was that the existence of these forms is useful, and it's defining our compactification geometry for us. But unfortunately, it's not getting us terribly far. So the things that we know is that J is a Hermitian 2 form. And this omega, if we're being mathematically precise about it, this guy in general is an almost complex structure. So unlike cases that some of us may be familiar with, this J is not closed in general, so these manifolds are not Kähler for general solutions. And this almost complex structure is not integrable, i.e. it is not a real complex structure, so the manifolds in question are not even complex in general. Okay, so that's true, but a pain. One thing that we did say is that the existence of this almost complex structure, sorry, yeah. Oh, do you?
So omega is 3.
Mm-hmm.
How does that define almost complex structure?
So you can contract, basically you can contract indices between these two to produce a 1-up, 1-down 2 tensor that, that squares to -1. But its Neuenhaus tensor does not vanish.
So you contract J with omega?
That's right.
Okay.
Yep. Yeah, we'll see this in more detail in the Clavial case in just a second. But sorry, other question? Okay. Okay, so far so good. What else do I want to say? One thing that is important here is that just in terms of the homology of this space, for SU3 structure, you can argue that the existence of this omega being nowhere vanishing and its index structure in the case of SU3 structure, tells you that the first Chern class of the holomorphic tangent bundle should be a little bit careful here. This is what I'm about to say is really relevant in the case that this is actually upgraded to a proper complex structure. But still, you can make an argument that C1 of Tx, which is related to trace of the curvature, is 0 in this case. And several people asked me last time, like, what about Stiefel-Whitney classes? Because I'm using the existence of spinners to derive all this structure. So surely there must be consistency conditions for having those spinners. And in this case, the vanishing of the second Stiefel-Whitney class is equivalent to the vanishing of the first Chern class. So indeed, you do get consistent backgrounds for spinners. But the spinners are not enough. You have a lot of other structure you got to worry about. OK, so far so good? All right. So where did we leave off? What we observed were examples. So we had EG1, which was the WIs all 0, and this corresponded to the Calabi-Yau case. And here we defined Calabi-Yau through many different equivalent ways: SU3 holonomy, Ricci flat metric, and this corresponds, as we'll see more about in just a second, to a Kähler manifold. Quick hint, this corresponds to dj being 0, and one that has C1Tx is 0. OK, so that was the easy case. I also mentioned to you briefly that, of course, you would be interested in the more general case. These torsion classes can be very arbitrary. You can have lots of different solutions with different topology and different properties of the physical theory. So you'd like to understand what happens when the torsion classes are not 0. Unfortunately, actually solving the equations of motion in this case is a big pain. So I mentioned the Fu-Yau type solutions, which are twisted S1 times S1 solutions over K3. I'll explain what I mean by this bad art in just a second with this geometry. These guys, in principle, do satisfy the equations of motion for the Schrödinger system. However, they are questionable physically. And the issue here is the regimes of approximation you use to write down the theory. So remember, I was doing alpha prime expansions. I want the scale of the physics that I'm interested in to write down the supergravity theory in 10 dimensions. I want this to be low with respect to the string scale. And so I need my expansion parameters to all be small. I need to have a sensible and self-consistent truncation of this theory. And what happens here is that the volumes of all these, this geometry, its overall volume as well as various subvolumes, are not free. They get fixed by general choices of flux, and they can be very small. So you end up with small volumes, which may or may not invalidate the approximations you made. Question over here?
Yeah, in the Clavial case, is omega the holomorphic form?
Yes. Capital omega is the holomorphic field form, and you have an actual complex manifold, so both complex and Kähler. Yep.
Do you care about the torsion classes?
Yes, I do, for sure. But I have not specified them yet. So if you tell me all the torsion classes, I can work out the higher Chern classes. We'll talk more about that topology in the Calabi-Yau case, for example, in just a second. But yes, I do care. In general, it'll affect the physics, but it has not been, it's not easy to just write down a closed form expression for them for general SE3 structure. Other questions? OK, good. So these guys, we had basically a couple of examples that we're not totally satisfied with. I should mention, just for fun, there's one other example that appeared earlier this year, which also looks good, but see also Fei et al. And this is 1703-10067. So these guys have a provocative title. They say that they made an infinite family of topologically distinct Schrödinger solutions. So they found a bunch of SU3 structure manifolds, they think an infinite family, all of them different, which, if true, in this question that I raised on the first day with my Venn diagram of what effective theories and stuff can I get, this would be an infinite set of effective theories that I could get from string compactifications, heterotic string compactifications. The hard part is these guys wrote down good solutions to the geometry. They failed to check that the gauge bundles, which I've been ignoring in this story for the Schrödinger system, they failed to check that the gauge bundles had structure groups that could embed inside either E8 cross E8 or SO32. So again, not quite physical. They actually don't for their examples. So these guys were mathematicians, and they solved the equations of motion. They have general bundles, but their bundles actually do not have vanishing first string class. And all the generators of E8 and SO32 are traceless. So you cannot embed the bundles that they wrote down into heterotic strings. Yep. Other questions? OK, good. So basically, what I want to take it from here is I want to now look at where we stand with these classes of solutions and how far we can push the questions of bounding and extracting physics from these geometries. So I finished with this. Why is this so hard? Why is it that I can basically write down only a couple of general SU3 structure solutions, and the couple that I write down appear to not be very physically interesting? Why is that so hard compared to the completely torsionless case of a Calabi-Yau compactification? And the answer here is the difference between so-called algebraic geometry, which does what it says on the tin. This is a definition of the underlying geometry using basically polynomial manipulations, versus differential geometry, where you have to solve nasty differential equations on weird spaces. Both are very fruitful and useful arenas of mathematics. However, this one, for our purposes, is way easier. There's also been a tremendous amount of progress in the last century in algebraic geometry that gave physicists a bunch of tools to address the questions we want to answer, which we just don't have at our disposal yet from a differential geometry point of view. So why is this happening? How is this distinguishing my two classes of solutions? In general, if you have algebraic varieties, the word variety here means just a space that you're defining through some polynomial equations. So something that looks like this, some polynomials and some equations. One class of these that we are going to use a lot with are so-called projective varieties. Hold that thought for just a second. But basically, if you think about things, geometries that you can define through polynomial equations, the observation for why this is hard is the only projective varieties with SU3 structure are Calabi-Yau. Full stop. So if you want to use algebra to define a space, you want to write down some equations in some space and describe something with it, which I will point out from back in the day in high school we're all really used to, right? In your algebra class you plot a bunch of functions, you know, you have some space, you write down things, you intersect them, you find points. We're all used to describing geometries that way through defining equations. If you want to play that game, you're not going to do it for arbitrary SU3 structure, you're only going to do it for Calabi-Yau. And that is why we understand Calabi-Yau so much better than general SU3 structure. Okay, very loosely, why is this true? So the SU3 structure, this guy implies that C1 is 0, as we described, the vanishing of the first term class. And algebraic varieties, i.e. things that we can write down in polynomial spaces in simple ways, these guys tend to involve complex geometry and Kähler geometry. And as we saw above from our definitions of Calabi-Yau, if your C1 equals 0 and Kähler, this implies Calabi-Yau. Sorry, I realize I'm writing too low again. I'll try and stay up. Okay, so with that observation in hand, that we have tools, polynomial tools, to address one type of compactification, not the other, I want to start with the so-called easy class of solutions, the Calabi-Yau solutions, which have been around in the literature for a long time. However, we're going to hopefully see that just recently there's been a lot of progress made in understanding the space of such geometries and some of their general properties in ways that have pretty big consequences for the physics. So this lecture is going to be mostly about Calabi-Yau's, and then we'll do the next 2 lectures on some variations away from that. Okay. So just a quick justification. Reasons to look at CY geometry first. We have a good toolkit in hand to extract physics, to be able to characterize the parts of the geometry that we actually need. And I will also try and emphasize that frequently, if you write down physics on a background that you understand well, like a Calabi-Yau, it is possible to follow that effective theory through a transition that actually takes it from Calabi-Yau to more general SU3 structure. So these are examples of so-called conifold transitions that I'll talk more about in this lecture, actually, a little bit later. So basically, you can take physics from someplace easy, and you can extract some physics from someplace hard in some cases. So these can be connected to more general geometry. I.e. conifolds. And one hopes to learn something about the physics. I should also say that just like the way that you learn a lot of mathematics, you need to start with a place where you have some tools. So like when you're learning differential equations, you always start doing linear differential equations first. When I was in undergrad, my differential equations professor said there's absolutely no reason to look at linear differential equations. It's just that those happen to be the ones we know how to solve, right? So said classifying differential equations into linear and nonlinear is like classifying the universe into bananas and non-bananas. It's true, but it's not terribly deep. So the same is, you can build this classification. The same is kind of true what I'm about to say. We're going to start with the bananas, and we're going to try and work out from there. OK. And I should mention, this is still hard, as you'll see. One of the primary obstacles is no metrics known, as I mentioned yesterday. So, I'm sorry? There are no non-trivial metrics known. So on tori, there are metrics known, but for proper, non-reduced SU3 holonomy, there are no analytic expressions for metrics known. There are numeric approximations, which I and other people have worked on, but in terms of writing down a closed form metric, this is hard. One reason, again, just to give you thinking about why this is tricky, right? If you've ever done a class in general relativity or cosmology, you know that you write down the metric and then you calculate everything else from it, right? And what do you do to try to find solutions to GR? You try and find metrics with a lot of symmetries, right? You start with your Schwarzschild solution or whatever. CY's manifolds have no continuous isometries. So part of the reason this is such a pain is that these metrics have literally no symmetries. So you cannot impose symmetry to make your life easier, which is, of course, one of our standard tricks. And that sucks. So this is still going to be difficult. They can have discrete symmetries, and I will come back to that. So those are actually very important for a lot of physics. They don't really help you hugely for getting the metric, although they do come into play. But there's a lot of physics that can depend on those discrete symmetries. Other questions? Need a U1 symmetry.
No, are they forbidden to have something?
Yep. Yep. So no continuous symmetries of any kind.
This doesn't apply to tori.
That's right. So tori are not proper SU3 holonomy. So several people asked that question yesterday as well. When you're talking about backgrounds, so we'll talk about products of tori in a second. You can have reduced holonomy compared to full SU3. I'm looking at proper SU3 holonomy for the moment. Okay. Absolutely. And the catch here is compact. So in order to really get a 4D theory coupled to gravity, which is where we're working at the moment with these equations of motion, this is where it's hard. If you write down non-compact geometries, many approximations and various features can be extracted, some of which are quite useful, but they don't solve the whole problem for you. Matt.
I guess while we're throwing caveats at you,
sure.
Of course, singular ones are known.
In some cases, yes. If you get very singular, you can. So I haven't talked about singularities yet. I'm going to come to that in a second. So far, I've been thinking about smooth manifolds. If you allow these manifolds to degenerate in various ways, so to get all spiky, then in some cases you can get symmetries that can help you out. Whether those symmetries survive the resolution of those singularities can be tricky as well. So let's come back to that in a minute. Okay. So what I want to do next now is start actually looking at Clavial geometry in more detail. So CY geometry has several important features that I haven't mentioned yet. There are two structures within the Clavial geometry that matter, two structures that are important, and you've seen them, I assume, many times before. These would, of course, be your Kähler and complex structures. So I'm going to do this very briefly, because this is one part of Clavial geometry that most people see many times over. So I'm only going to do the quick summary. There is a complex structure, i.e. the statement that we can take our real 6 manifold and turn it into a complex 3 manifold. And this guy can be written as Gij in the Clavial case, Gik, Jk, J, where J is defined from before for our general SU3. And this guy, Jij, can satisfy J squared is minus 1, plus so-called integrable. This is a global consistency condition that says on patch to patch you have a notion of the number I on a compact manifold. So the existence of an integrable complex structure says that M6 is a complex manifold. Let's call it X, possibly X3, just to avoid any confusion. So here I defined the complex structure by contracting with the metric, almost complex structure. You can also do this for more general SU3 structure manifolds by contracting with omega. But, okay. Sure.
Does that mean G, the metric, can be constructed on omega?
Yes, I mean there's various contractions can give you relationships that allow you to get back and forth. So there's an alternate way. The reason I'm not writing it down is I actually don't remember it off the top of my head. I can look it up for tomorrow. But there are ways of defining J purely in terms of just this guy, sorry, 2 index up down J in terms of this guy and omega. In the Clavial case, this is the standard way.
Can you explain again what in the J squared is defined? What's the other?
Integrable? Okay, so integrable is, technically this is the vanishing of the so-called Neuenhaus tensor, which is a big bilinear tensor in the J's, 2 index J's. What does it mean physically? You have a complex manifold, or you have a compact manifold that has different coordinate charts, right? So what this guy is giving you is it's giving you a notion of I, right, a complex number. What this integrability condition is giving you, this is not going to be written the same way in all coordinates at all points on the manifold. So this integrability tells you that you can move from patch to patch in a way that's compatible. So you can patch complex coordinates over the entire manifold in a sensible way.
I think I missed the equation. That's
Another condition. Sorry. I just understood the confusion. Sorry. Separate idea there. Squares to minus 1 and is an integrable complex structure. Sorry for the confusion. Other questions? Okay. Cool. So that's the complex structure. So the physical idea is really simple. Clavials are always going to be complex manifolds. And the Kähler structure so this is the statement that Dj, our Hermitian 2 form, is also closed. This implies that the Jij, remember we built him as eta dagger gamma ij eta from our spinner. This is called a, quote, Kähler form on the manifold. And it tells you that the metric has a very particular form. You can write it in the complex coordinates that are available to you as something that looks like so, bar B bar. So you can write the metric as in complex coordinates, 1 barred and 1 unbarred index, so a 1, 1 type metric. the both barred or both unbarred components of the metric in complex coordinates are 0. And importantly, the closed condition here tells you that GAB bar can be written as two derivatives of some function f, where this guy is called the Kähler potential. So this is an incredibly useful structure because it says, even though you don't know what it is, the metric is really pretty simple. So it can be entirely defined by some function, f, the Kähler potential. You take a holomorphic and anti-holomorphic derivative of it, you can reconstruct the metric. Okay, so to see more about why these structures arise, why they're important, how you put them in the general framework, I would like to refer you to some standard places in the literature. So looking at all of these guys in the context of general SU3 structure manifolds, so under what conditions can you get either a Kähler or complex structure from SU3 structure, I recommend the paper I mentioned yesterday by Guerrieri. This was FDH 0211102 with the right number of ones this time. Also a great reference, and I'm going to put this up on the wiki for you. There's some lecture notes by Philip Candelas from the 1980s, 90s, a long time ago, that are not on the archive, and they're one of these great passed down from student to student kind of things. They go through everything you would want to know about complex and Kähler geometry, and there are many other references, of course, Green, Schwartz, Witten, other places you can read about this in a physics-friendly form. I'm not going to go into great detail on the ingredients here of complex and Kähler geometry, because this is just written down in a ton of places. So this is something that is easy to look up if you want to find. So importantly, these structures used to lead to a characterization of metric fluctuations. In the Clavial case. Specifically, what you can show is that if you have a starting choice of your metric g, and you perturb that, so you take your initial metric plus some fluctuation of g, things that you can see are that GAB bar, as we said, is the only non-trivial starting point that we're going to consider, and the delta g's come in two types. And I'm doing this very schematically because, again, I assume you will have seen this, and it's easy to look up in detail. The delta g's come of the type a Kähler variation or a complex structure variation. So these two structures that come from the manifold, the fact that the metric has a Kähler potential and can be written in a specific way, the fact that there's a complex structure on the manifold, if you vary either of those things, that's equivalent to varying the metric on the Clavial manifold. And you can invert these two processes, and every metric variation that you want to write down can be written as a variation of the J or a variation of the omega. So these two fundamental guys that we're playing in SU3 structure, they can be used to just characterize every way that the metric can change and preserve your equations of motion. So specifically, what you can show is, let's do the complex structure first. Complex structure, if you take Jij going to Jij plus some change, let's call it tau ik, in real coordinates, this ends up telling you that in complex coordinates, this has the form of one barred, one unbarred index. These guys live as a form. It turns out they have to be closed. And this index structure tells you that this is an element of cohomology. Specifically, these are closed but not exact forms valued in the holomorphic tangent bundle of the manifold. And for Calabi-Yau's, this leads you to the so-called Hodge numbers of the manifold, which I imagine everyone has seen before. Similarly, the Kähler structure goes in entirely the same way. So similar. For Kähler structure, you can show that the variations in the Kähler structure live in H1 Tx dual, which are related to H11, the Hodge numbers of the Calabi-Yau manifold. So you will have seen these two types of forms used to characterize Calabi-Yaus all the time. Somebody says, I'm handing you a Calabi-Yau. You say, how many variations of the metric are allowed? How many ways can I change the complex structure in the Kähler structure? And that tells you something fundamental about the manifold. Intuitively, again, I'm sure you've seen this before, but intuitively, what are you changing about the metric when you do this, or changing the space as you do these fluctuations? Intuitively, complex structure variations correspond to changing the shape of the manifold in a way that I will make more precise momentarily. So you're changing the shape as a complex manifold, and the Kähler variations correspond to changing volumes. So in simple cases, there may be only one way that you can vary the Kähler form, which corresponds to a metric fluctuation, which is changing the overall volume of the manifold. So just how big are those, the overall extra dimensions for your 6 manifold? That one's always available to you. But there can be many subvolumes. So if you think about like a block of Swiss cheese, you don't just care about how big the block is overall, you care about how big the holes in the Swiss cheese are too. So there can be lots of subvolumes here, many different modes in the Kähler moduli. Those volumes can also vary, and you care about those too. Okay, note about these moduli. So CY manifolds have this pair of Hodge numbers, H21 and H11, and these guys are not 0 for the examples that we really understand with SU3 holonomy. There are always wiggles that you're allowed, which can fluctuate the metric and preserve your equations of motion. So yesterday, when I stated Yao's result, I talked about unique Ricci flat metrics. That was a little bit imprecise, as Matt was asking me about at the time. The statement is that within the families of possible Kähler and complex structures, if you choose one, there is a unique Ricci flat metric on the Calabi-Yau associated to that. If you vary the moduli, vary the complex and Kähler structures, the metric will change too. There's not just one metric that will solve your equations of motion, but if you choose these auxiliary structures, then there's a unique metric. Does that make sense? Okay. So these guys are used to characterize. These numbers appear in the 4D theory. So I used the word already, moduli. Moduli because from a geometric point of view, I can wiggle the metric and still preserve my equations of motion. Of course, as physicists, we know another definition of moduli, which is flat directions of a potential. And it turns out those two notions of moduli are the same. So these appear in the 4D theory as massless scalars. We'll see more about this in a second. And there are a lot of them. In general, order hundreds for a Calabi-Yau manifold. So if you're talking about generic predictions of the effective theories that you write down, if you're just writing down Calabi-Yau compactifications of heterotic or type 2 theories, you will end up with a whole lot of moduli, a whole lot of massless scalars in your theory that may not be so great for whatever physics it is you want to describe. So these guys can be problematic. I should say, again, comparing to general SU3 structure manifolds, those guys do not have these wiggles available in the metric. So in general, they're not complex manifolds. The volumes of non-Kähler manifolds are also fixed. So this feature is one that's sort of a problem with Calabi-Yaus. More general compactifications may do better on this. Okay, so we'll explain in just a moment why the two notions, I should say, the word moduli is going to appear here, and I'll come back to the two notions, geometric and physical notions of what moduli mean. I should also say that so far I've just talked about the metric and a basic feature of the manifold. Once we start thinking about what we want for the 4D physics, there's a heck of a lot that we actually are going to need to extract the physics that we care about. So things that we need, other things we want. We want more info on CY geometry. What kinds of features can affect the physics that we care about? So things that we want include substructure. What do I mean by that? I mean basically subvarieties of the manifold. So if you have a 3 complex dimensional manifold, you could consider 2 complex dimensional submanifolds, one complex dimensional submanifolds, in general subcycles. These have the form algebraically of divisors, curves inside the Clavial, all of these guys inside X. For example, they could be non-complex subvarieties, so special Lagrangian subcycles. All of these are things that we could wrap brains on. So the existence of subcycles or substructure in the geometry tells you a lot about the non-perturbative effects that are going to enter into the theory, which we haven't discussed yet. Other things that you care about are symmetries. So we already had the question, there's no continuous isometries. Can there be discrete isometries? And the answer is yes, and those discrete symmetries can play a big role. So these can be discrete groups that act on the manifold. These can contribute in heterotic theories to things called Wilson lines. These are a manifestation for the gauge fields of the Aronoff-Bohm effect from electromagnetism. So these are examples where you have a non-trivial gauge field with a trivial field strength, which can still break symmetry and affect the low energy physics. Of course, more generally, you have things in type 2 theories like orientifolds, flavor symmetries in the 4D physics, family symmetries, R symmetries. All of these can be affected by the existence of discrete isometries, and the list keeps going on. So, etc. The more detail we have about this manifold, the better, and almost every geometric feature that you can think of will have a consequence in the 4D physics. And that's where I'm going to try and go over the next couple of lectures, is showing you what some of those are. Okay, so with that in mind, we want to know a lot of stuff about Clavials, and we want to understand how many Clavials we can write down, and whether we can say anything about generally constraining / bounding the geometries and the types of physics we get. Yeah?
You said something like there's more variations in the Clavial case and the general case. It's a little strange, but I thought Clavial was
That's a great question. So there are other things that can, excuse me, can vary. So the torsion classes, for example, can be chosen differently, right? You might say I have like arbitrary choices of torsion class in the general SU3 structure. Those choices, generally in terms of the topology of the manifold, end up being discrete choices. What I'm describing in the Clavial case here is continuous fluctuations. So basically, you try and write down the geometry, and you say, how much can the geometry wiggle? The amount of wiggles that it gets in the Clavial case is way higher than in anything else. This is basically because it is, this is a loose answer, but from the point of view of SU3 structure manifolds, this is a space. I'm going to use the words with a lot of symmetry, right, by setting all the W's to 0. Not symmetry in that the manifold doesn't have symmetry, but it's a very simple case of SU3 structure, which just gives you more freedom to satisfy the equations of motion. In general, if you write down a bunch of arbitrary W's and you try and change them, getting that tuning to work is so hard that there's very little fluctuation that's allowed, if that makes sense. So you're saying, could I talk about non-compact special? I talked about non-complex. I just meant non-complex subcycles. So these are, real. Great. So I'm actually going to do the Hodge numbers for fourfolds next in just a moment. So there's actually more topology. Here, everything I said was a specialization of SU3 structure to SU3 holonomy. The question here is, what happens if I, instead of starting with a 6 manifold, I'd started with an 8 manifold? And we'll come back to that. I could also ask about Clavial 5-folds as well. We'll do that in just a second. But the topology here is specific to 6 real dimensions, 3 complex dimensions. Other questions? Okay, good. So let's ask the following questions. We want to know, 1, how to build CY manifolds explicitly and in as general a way as possible. And 2, how many are there? Is there an infinite number? Can their properties be infinitely different? Can this lead to effective theories with wildly different characteristics? How do we characterize them? So these are our questions, and we're going to begin with one. So how do you build them? There are basically three tools, or let's call them approaches, to building Calabi-Yaus. And every manifold that has been built in the literature has used one of these main three approaches. The basic idea is to start with really simple geometry. And then use it to build complicated geometry, i.e. the Calabi-Yau. And the three types here are three ways of taking simple and making it complicated. So let us go through those approaches. So the first one is by far the simplest. This is the notion of algebraic varieties, which I've already mentioned, i.e. define a space via some polynomial equations. So the basic idea, let's embed x Calabi-Yau inside some ambient space, let me call it A easy. And I want to do that via, in the coordinates of the ambient space, I want some set of polynomial equations, all of which have to equal 0 in the coordinates of A. So the PI's are going to be some general polynomial XA, where XA are coordinates on curly A. In this case, topological data of X will actually be determined. So topology of X will be determined by the choice of the A plus the polynomials. Okay. Here, just a quick example that, again, many people have seen. For example, the quintic hypersurface in P4, everybody's favorite and first exposure to a Calabi-Yau. I'll define what this means in just a second, is of this type. So this is one approach, which is extremely easy and used all over the place. Another one, which is going to prove very fruitful, it has actually a lot to do with the lectures that you're going to be hearing about on F-theory next week, is a tool called fibrations. So the basic idea here will be to fiber one simple geometry over another. Now, probably many of you have seen this before, but I'm going to define just what we mean by a fibration. So the definition of a fibration is a continuous mapping from one space to another. Let's define this map by the function pi, which takes me from space x to another space, let's call it B, such that for, I'm going to write for all, for almost all points B inside this target space B, the inverse image of B is homeomorphic to the inverse image of B prime for all other B prime in B. And this property is referred to as homotopy lifting, i.e. the inverse image of any 2 points in the target space are, quote, homotopic, which just means smoothly deformable. So the inverse image of any 2 points in this space looks really similar, is what we're saying. Here, the inverse image of a point in the base, pi inverse B, is referred to as the fiber, and the target space B itself is called the base. Okay, that is a formal definition. Great, let's actually make it intuitive, because you've seen this all over the place already. So this is where my bad art comes in. So fibrations are basically the notion of you want to stick one space, quote, over another space. Over being the x, the fiber goes over the b, which is the base. So let's remind ourselves why this is actually an easy idea to stack up geometries in this way, and will prove useful to us. Okay, so some examples. We need some space, fiber, over every point in base. And I'm drawing one on top of the other. Let's be more specific. Here's an example of a very simple fibration. R2, about the simplest space that we can imagine, is an R fibration over R. Okay, that's pretty easy. Let's think about what we mean by R2. So I have my two-plane. It's saying pick any point in the space. There's one. There is a natural mapping from that space down to a point in what I'm calling the base. So here, B is the x-axis. So I can map from a general point in x, the entire R2 plane, down to the x-axis. That's the base. And if I look at the inverse image of this point, every point that's on a line above this will all get mapped to the same point in B. So the inverse image of a point is another copy of the real line. Okay, that's pretty obvious. Here's another example, very similar. The cylinder is an example of a AB equals interval fibration over S1. So what am I doing here? Take any point on the cylinder. You can map it down to a point on the circle. You can choose where you want that circle to be. So just cut the cylinder at some point. Inverse image above that point will be an interval. So for example, the length of the cylinder. Okay, these are both examples of fibrations that are actually super trivial. These are not just fibrations, these are products, right? So the cylinder is the product of an interval and an S1. R2 is also the product of two copies of R. This doesn't have to be the case. You can have non-trivial twisting in your solution. So EG3, and I have to apologize ahead of time. I am artistically handicapped, so this is not going to turn out well. But let me try and draw a Mobius strip for you. Yep, it didn't turn out well. Yeah. It's not going to get better, but I'm going to keep working on it. And oh, that's terrible. Okay, use your imaginations. Mobius strip. What's going on with the Mobius strip? The Mobius strip is the cousin of the cylinder. So what's happening to the Mobius strip is it's again an interval fibration over an S1, but instead of having the fiber look the same at each point over the S1, it non-trivially twists as you go around the Mobius strip. Turns out these are the only two ways to fiber an interval, or in fact a line, over the circle. And they're related by a Z2. So you can either do a twist. An even number of twists will give you a cylinder. An odd number of twists will give you a Mobius strip. So this guy is a, quote, non-trivial fibration. Non-trivial in that there is a twist to it. And the twist is pretty intuitive. We've all played with Mobius strips as a kid. You hook them up. In these two cases, there is no twist, so these are just trivial fibrations or products. Okay. So far, so good. Let's put that up there. There's one other important distinction I need to make about fibrations, because I'm going to use it later. So far, I haven't really distinguished two features that are very similar. All the structures that I just told you about are actually the same for a so-called bundle as they are for a fibration, with one important difference. So everything I've described so far, the fibers over each point look literally the same. So in the cylinder, if I look at any given point on that circle, I look at the interval above it, it's literally the same. Same for the Mobius strip, same for R2. However, in my definition, I say that I want this to be true, this property that the inverse image of any 2 points in the base is the same. This has to be true for almost all points for a fibration. So it is actually possible to have some fibers go funky. So if this is my base manifold, let's say I have a T2 fibration over something. So I'm going to draw a bunch of tori over different points in the base. It is possible to have one torus go weird. So weird torus here. At this point, this is called a degenerate fiber. If everybody is a smooth T2, that's still okay as a fibration. It is not okay as a bundle. So if somebody describes a bundle, it has all the same features, something's over something else. But the bundle, every fiber is literally the same. For a fibration, some fibers get to go weird. And this will play a really crucial role in F-theory, which you'll hear more about in all the lectures next week. OK, so that's the 2-second version of fibrations. So why do we care for Calabi-Yaus? Well, it's just like I can take an interval and an S1 and I can build a Mobius strip, which is a more complicated object. For Calabi-Yaus, you can take two very simple objects, fiber one over the other, and build a Calabi-Yau. We'll see that more explicitly in a moment. And finally, the third tool that I need to talk about is so-called surgery. So what is the idea here? Idea, start with an easy space. X easy, let's call it. And then what we want to do is perform surgery to locally patch in another space and glue it to some points in the original one. Locally patch in another space. Let's call this guy Y easy. And that leads us finally to a more complicated space, X prime. So the picture here is you start with some initial smooth, easy-looking space. You pick some subvarieties of it. So here I've drawn a line and a point. This is X easy. And you decide to replace this line and this point with some other space that you're going to glue in at those locations. Mathematically, this is the process of blow-up or resolution, which we'll talk in detail about just a few minutes. And what you end up with is a version of the space where you now have a new geometry that has been pasted in at all the points you originally chose. So for example, I might choose to put in 2 spheres. I can take a given point, cut it out, and replace it with a 2-sphere. That changes the features of my space by just gluing one geometry into another. You can decorate it and make more complicated objects. OK. In general, in order for this to work, ways that this appears, so the EG here, the way this is normally done is to start with a singular Calabi-Yau. So a Calabi-Yau manifold that looks a bit weird at some points. And the points that you choose to replace are singular ones. You can patch in easy spaces and give you a new smooth Calabi-Yau. So for those of you that have seen this before, conifold transitions are exactly of this type. You can start with one manifold, singularize it, fix the singularities, and end up with a new Calabi-Yau. This is a really important way of connecting two different geometries, and we'll look at this in more detail in just a moment. So basically, every Calabi-Yau that we know how to build has been built through one of these 3 approaches, either an algebraic variety, building it as a fibration, or performing surgery on the manifold to fix it up. The only exception to that, which I don't want to talk about in detail yet here, is actually a notion of quotienting manifolds. So this is quotienting manifolds by discrete symmetries, which we talked about earlier. This is basically performing origami on a Calabi-Yau. So you start folding the space, identifying various points on it. You can generate new Calabi-Yaus that way. I'll come back to that if we have time, but that's a much more rare procedure for building new manifolds. OK, any questions at this stage? Right. Good. So I want to begin with one. And I want to start building these guys and then seeing what we can say about them. So let us begin with approach number 1. And we want to build Clavial manifolds as algebraic varieties in easy spaces. So, to begin with, we have to choose the easy ambient space where we're going to write down some polynomials. What is the easiest complex manifold you can think of? Go on, be easy. Cn, yeah, that's my favorite too. So first thought, you want me to pick an easy complex space? I like Cn. That is very easy. It has a problem though. It is non-compact, right? So if I write down general equations in that, they're going to have non-compact solutions, and I'm really interested in compact ones because I want to get down to 4D theories. So what I need is a version of Cn that is compact. It's a manifold. And happily, such a thing exists. So first thought, Cn, but non-compact. So the question is, can we make it compact? So what you want to do is you want to take your points at an infinity and you want to wrap them back around to touch each other to make it into a compact manifold. So the fix is a manifold that is known as CPN, complex projective n space, which does exactly what I just described. You just take points at infinity and wrap them back around. The way that you define this guy is you say, I have a bunch of coordinates on it, let's say z0 up to zn, and in order to get rid of the points at infinity, I'm going to identify points on this space up to scale. Where the scale is not 0. So any given ray in this space, I'm saying if I can scale along that ray, I want to collapse that entire ray that can go out to infinity down to a single point in the space. This is what CPN does for you. That's the projective key here. Frequently, I should say notationally as well, people just drop the C. So this is written frequently as PN. That might be confusing. Is this real projective space or complex projective space? In physics, we always care about the complex ones, so there's no confusion. People just write this as PN. Let's do an example to see where this works. So let's look at P1, the complex projective 1 space that has two coordinates, z0 and z1, which are identified up to scale, leaving me with one complex coordinate left in the game. And this space has a very simple interpretation. This is actually just the two-sphere, as you might imagine. So it's like, as a real manifold, you take the real plane, you identify points at infinity, you turn it into S2. Here, in the two-sphere, the poles are where weird things happen and you have to define different patches. The point, note, z0, z1 equals 0 is not in the space. And S2 as a complex manifold is just a complex one manifold, which is what we mean by this projective space. You can do this, so it's easy to think about S2 because we can visualize that one. Pn has very similar features. It's an n-dimensional complex space. Again, these scales tell you that it's compact. Okay, so far so good. So that's pretty easy. Compact versions is Cn for the win, and then we can just write down algebraic equations in them. And this is, of course, how people got started writing down Clavials. Okay. So what we want to use then is take we want to take a easy to be Pn, and we want to ask, can I build a Clavial as a polynomial P of Zi equals 0 inside Pn, and can I make it Clavial? That's going to be the first question. So if we do this, if we define a manifold via the 0 locus of a polynomial of this type, the notation that people write, and I've already written it for the quintic, you've probably seen this before, is people write the following with brackets. The first thing tells you the ambient space you've chosen. I've chosen a projective n space. The brackets tells you the degree of the polynomial equation. So here m is the degree of polynomial equation. And this is a homogeneous polynomial. Homogeneous poly. Anybody have any insight into why, if you're dealing with space that has a scale, like I just described, why is homogeneous polynomials important, i.e. every term is of the same degree? Otherwise, it just doesn't even make sense as an algebraic equation, right? So if I have here, like say I had z naught plus 1 equals 0, just making up something that's not homogeneous, and this guy can scale by any lambda, what do you mean by the solution to this equation? This isn't even well defined as algebra. So the only equations you get to write down are homogeneous equations. So for example, in P1, I can write down things that look like z naught squared plus z naught z1 plus z1 squared, blah, blah. And what would be the solution to that? This guy, every term scales the same way as 2 copies of the lambda, and so its 0 locus is unaffected by the scaling. The scale drops out of this equation, and so I have a well-defined algebraic solution. This guy, what would be the solution? This would just be 2 points, right? This is a complex line. This is a quadratic equation, so I would get 2 complex roots to that equation, and they'd be well-defined roots. Okay. Now, here's the game that is fun. Pn, as this simple warm-up, this has a natural Kähler metric on it that lives on the projective space and respects all the scales that are in play. This is called the Fibini Studi metric. And it has the following form. GAB bar can be written as 2 derivatives, dA d bar b, of the natural log of the mod squared of the coordinates up to zn squared, where here this mod squared is zz bar terms to make this real. This metric is well defined on Kähler on any projective space. It makes sense as a good metric on projective space. And of course, if I have that on the ambient space, I can restrict to the polynomial pi equals 0 locus in Pn, i.e. this is an algebraic, our space that we're trying to build, X, is an algebraic subvariety of the projective space. So it's a metric subvariety as well, so you can just restrict the metric in the normal way, as in GR. But of course, there is a catch. And this is my first slightly sadistic homework exercise for you. Sorry, I say slightly sadistic because it's hard. It's just tedious in GR. But it gives you a real appreciation for algebraic geometry if you do it. You can ask, under what conditions can that restricted metric on something as simple as projective space do what I want to be a Calabi-Yau? So if you feel inspired, you can show, and this is homework, that if you take the Ricci curvature, Ricci scalar, associated to the Fibini Studi metric, and you restrict it to X, your Calabi-Yau hypersurface, or not yet Calabi-Yau, but just hypersurface, any hypersurface defined by a polynomial, what you find is that it has the following form. It can be written as curvature restricted gives you the metric, Fibini Studi metric, so this is the 2-index Ricci tensor, is proportional to m being the degree of your polynomial, n the order of projective space, so complex n space that you've chosen, and it will be of this form. So you can see if it so happens that m is equal to n plus 1, then you can show that trace r is 0, which implies that C1 of X is 0, which, if it's Kähler and has vanishing first string class, that was one of our definitions of Calabi-Yau, that implies it's Calabi-Yau. So any polynomial equation that is of a degree that is one more than the projective space that I want to write down will have a vanishing first string class as a projective variety and will satisfy the Calabi-Yau condition. So any subspace of projective space can generate a Calabi-Yau if it's of the right degree. So this implies that X is a Calabi-Yau. Now, why do I say this is a good exercise to go through? This is how you algebraically, not even algebraically, this is how you, in general relativity, actually compute the curvature, restrict it, and show that the trace of curvature is 0. There are some much easier ways of showing algebraic varieties have vanishing first string class. This is where algebraic geometry comes in. But having to do this by hand in at least one case gives you an appreciation for some of these more advanced tools. So let's do some examples now. This being true, I want to build a Calabi-Yau threefold. Here's everybody's favorite one, P4, 5. So this is a 4 complex dimensional compact manifold. One equation in it. That drops your dimension by 1. That's a complex 3-dimensional manifold. Here, the degree of my polynomial m is 1 plus the projective space that I worked in. Therefore, it's Calabi-Yau. So the quintic is a Calabi-Yau manifold embedded inside P4. Cool. There's one. All right. Can we do any others? So this guy has a homogeneous equation, right? Looks like z0 to the 5 plus z0 for z1 plus every possible term you could think of. Quick aside, and we'll come back to this in more detail. When I said earlier that the complex structure tells you about the shape of the manifold, you can show that there's 101 different coefficients to the polynomials that I could write down that are homogeneous and of degree 5 in P4. Those actually correspond in this algebraic case to the complex structure. So as you change the defining equation here, so if I wrote this as this one's 5 and this one's 2, if I vary these numbers, that's changing the complex structure of the manifold. And this is giving me a family of metrics. So this is not just one manifold, but for each choice of algebraic equation, I get a different one in the same family. So far, so good? OK, so let's do a quick exercise then and see how many more we can build. And this is fun because you can see the structure pretty quickly. So an easy generalization is to have more than one equation. So in P4, there is exactly one way to get a Calabi-Yau. I write down a degree 5 equation. What if I up the dimension of the ambient space a little bit? So let's say I wrote down P5. If I had 2 equations, I can get that down to a 3 manifold, right? So if I wrote down this guy, 3, 3, for example, this is the 0 locus of 2 polynomials, P1 of degree 3 equals 0, and P2 of degree 3 equals 0. The complete intersection is what this is called. So complete intersection of these polynomial equations will give me a Calabi-Yau. Complete intersection here means choose P1 and P2 to be totally general. If it's not a complete intersection, like they could be the same, right? If they're both the same, then this would actually just be one equation. So I'd only drop myself down to a 4 complex dimensional manifold. So if you choose them to be general, it's called a complete intersection. That would give you a 3-dimensional manifold. And again, the sum of degree rule here works. So here I add up the degrees. Sum of degrees equals n plus 1. There I wrote it just for one polynomial degree. So 3 plus 3 is 6. That's one more than 5. That works. That's Calabi-Yau. OK, you guys' turn. Give me a couple more. What's another one I could write down? Can I do any others in 5? Sorry. 2 and 4. Sweet. Any others? You guys are like, I can do partitions. Yeah, you can. But I actually am getting to a point. So any other partitions that I might do here? Sweet. 1 and 5. All right, let's check out that guy. P5, 5 and 1. Anybody spot anything worrisome about this one? Sorry? I heard somebody saying something. Degree 1 polynomial is kind of trivial. So let's think about that. A linear in the coordinates of P5 looks like z0 plus z1 up to z4 equals 0. So what I can do with a linear is I can just use it to solve for one of the equations, sorry, one of the variables. So let's say I can always choose the scale to solve this guy for z0. So z0 equals linear in terms of the rest of the zi's. It's still going to scale the same way. So if you solve a linear inside a projective space, all that's doing for you is actually reducing the projective space by 1. So that is the statement that Pn of degree 1 is always equal to Pn minus 1. So I can write this down. But this guy is back to the quintic. This is actually P45. Because you have imposed a linear first, you drop the dimension of the projective space by 1, back to the quintic. Okay, with this in mind, how many more? There aren't that many more I can write down. Can I do 3 equations? So P5, you want to do, sorry, you said P6. 2, 2, 3 was 1. That one indeed is true. That's another Clavial. 6, 3 equations is 3. Sum of degrees. Anything else? So we can't use linears, that's the rule. So this is just about integer partitions. I have to get a 3 manifold. I can't use any linears in the equations. How high can I go? You know? Oh, sorry. Here it's P6. So P5, we had these 2. In P6, we have 1 more. 5 and 2. Okay. So you want to do P6, 5, 2. So here's the problem here. I've got in P6, 5 and 2. That's 2 equations in P6. That's a 4-fold. So it's a good manifold, but it's not 3. So that's good. Any others that can give me 3? Good. In P7, I can write down 2, 2, 2, 2. 4 equations, not involving any 1s, in P7 gets me down to a 3-fold. And that's it. I am actually done. So if you're writing down simple projective varieties, i.e. polynomials as a complete intersection of just a bunch of polynomial equations in the simplest complex space we can think of, we've actually listed in real time all the Clavials that you can write down. The quintic, 2 here, 2 here, 5 in total. And these guys get a special name because they were the very first things that mathematicians wrote down. These are the so-called cyclic Collabos. Cyclic because they all have a special feature, which is they have exactly 1 Kähler modulus, because they're defined in 1 projective space. So the only degree of freedom in the metric that changes the volume is the overall volume for this 5. And these are the only 5 known that have that property that are built as algebraic varieties. Okay, so does that mean there's only 5 Clavials? No. We have to generalize what we're looking at just a little bit. So how can we generalize this setup? There are several main ways we can do that. But happily, once you see how to do it for something as simple as what we've just written down, you can see how this can be done very systematically. They're the only algebraic ones with h1 equal to 1. You can get things with h1 equal to 1 via quotients, which I have not talked about here. Okay, so good. So generalizations. There are more than 5 Clavials, so what gives? More that can be constructed as algebraic varieties. One way to generalize this is to use direct products of simple spaces in A itself. So thinking about products, we had good luck with that with Rn, right? You can take Rn, you just take direct products of R cross R cross R cross R. You can make bigger and bigger ambient spaces. So for example, if I take A to be P1 cross P3, this is, this way, if I take this direct product, this is a compact complex 4 manifold that is not equal to P4. So unlike Rn, when you take copies of R and you multiply them together, you just get a bigger Rn. The same is not true of projective spaces. So if you take 2 different projective spaces and take their direct product, this is in the normal sense, just like you'd have x, y coordinates on the 2-plane. You're just saying you have vectors of coordinates where x comes from here, y comes from here. But this is not equal to P4. And you can see that because you've got 2 scales, not 1. Right? So there's a scale here that identifies all the coordinates. There's another scale here. Here there's only 1 scale that makes your coordinates compact. So for example, you can play this game where you take various products. So as an example, I can write down the following notation. These guys get stacked on top of each other to denote this product structure. I can write one equation in the ambient space P1 times P3, where now it has a multi-degree. I have to be homogeneous with respect to the two scales in my ambient space. And that degree goes in the brackets again to tell me that it's a Calabi-Yau. So this would look like, if I call the coordinates on the P1x and the coordinates in the P3y, this would look like x naught squared, y naught to the fourth, x naught, x1, y naught squared, y1, y2, many terms equals 0. So this is a homogeneous degree 2 in the x's, degree 4 in the y's polynomial. I can write down in that product space, and I can define a Calabi-Yau with that. You might say, okay, just like we started enumerating the different guys that we could do for a single projective space, if you allow yourself arbitrary products of projective space, so you let A go Pn1 as many times as you like up to Pnp, say, if you have an arbitrary product, how many different algebraic equations, complete intersections, can you write down in products of projective spaces that can give you Clavial manifolds? And this, in a feat of remarkable computing in the 1980s that was done on magnetic tape at CERN, Philip Candelas actually wrote down an algorithm to generate all of these guys. He figured out when they'd be redundant, just like we did with that linear in a single projective space. And it turns out you can build 7,890 manifolds of this type. So instead of the 5 that we could just write down on the board quickly, there's a few more, and it takes some computer power to do. But this is still not a huge number, and you can write them down. Okay, what else could we do? How else can we change the game? Well, the idea that we used was basically to start with our simple complex space, which was just Cn, and then we introduced the scale in order to make it compact. So it turns out there's different ways to introduce that scale. So we can change the scaling relation on the coordinates. And you can also get a compact space if, unlike, see if it's still written. Did I write it? Nope, I've erased it already. Unlike what's happening in these coordinates where everybody scales the same way, so everybody gets the same power of lambda that identifies them, what you can do is have coordinates that scale differently. So rather than z0, z1, z2 going like lambda, z0, z1, z2, for example, what you can do is have z0, z1, z2 get identified where each guy scales his own way. Lambda z0, lambda squared, z1, lambda cubed, z2. This will still give you good polynomial equations as long as you write down homogeneous equations. And I see that I'm almost out of time. As long as you write down homogeneous equations of the right overall degree, this will still give you Calabi-Yaus. And this is called a weighted projective space. Let me just finish with this. So here, in weighted projective space, here you have the sum of the weights has to add up to the dimension plus 1 in the usual way. Or rather, sorry, let me just say it this way. Dimension has to be, this has to be the degree of the polynomial. Okay, that makes more sense. So for example, here this would be CP2, because I have 3 coordinates identifying 1 to a scale. That gives me a twofold. Here this is weighted CP2. So for example, this is written as P1, 2, 3, where I'm telling you the weights of each coordinate as the subscript. And if I write down a polynomial of degree 6, which is homogeneous with all the right terms in x, y, and z, this guy is a Calabi-Yau one-fold. 2 complex dimensions for the ambient space, 1 equation. This satisfies the Calabi-Yau condition. So anything of this type where you vary the weights works. And you can take products of these guys, products of these ambient spaces. You can write down polynomial equations in those. The general form of this type of approach, which I'm not going to get into in great detail, but you're going to see more about from Professor Weigen next week, is toric geometry. And if you ask, how can I build, say, just one equation, just a hypersurface in something that has this general kind of scaling of the coordinates, This is called a toric hypersurface, and there are 500 million examples known of this type. So you can see this is getting big fast. We went from 5 to 7,000 up to 500 million. I'm going to pause there because I think that everybody needs lunch fairly rapidly here. But where I'm going to take off with next is how can we take what we learned so far, this is just how we know how to construct things, what can we say in general about Calabi-Yau, and what can we say about the finiteness of the set of Calabi-Yau? And that's where I'll pick up next lecture. Thanks. Questions before lunch? Everybody's good? Okay. Have happy lunch.
So maybe you have explained in the class, I didn't listen clearly. So why P7 like 2, 3, 3 doesn't work?
Sorry, so you say P7?
Yeah.
And I want 2, 3, 3. So this does work. This is a Calabi-Yau, but it's a 7-dimensional complex ambient space and 3 equations. That's a